So now that we've seen how the computer hardware and the operating system can work together to provide what we call the trusted computing base, we're going to start to look at some details on how we can evaluate and eventually certify a specific level of security that we can be assured our computer system will afford us. We're going to look at what's called the TCB, or Trusted Computing Base. We're also going to then consider something we've already talked about a few times. This is the execution or security domain. Remember, this is the collection of all objects that a subject has access to. We've also referred to this as the user profile, the user's level of privilege as well. We're also going to look at a couple of components in the operating system. We've already mentioned the security kernel, and I believe I even mentioned the security reference monitor. We'll be delineating that a little bit further. And then we're going to look at some details related to the security kernel that are required so that this level of security can be evaluated, tested, and then certified. So the Trusted Computing Base. This is a term coined from the Orange Book. Now, the Orange Book is a collection, it's one of in a collection of books called the Rainbow Series that was developed by the National Center for Secure Computing, the NCSC. And the Orange Book defines if we have a computer system that we recognize is going to hold our valuable information assets, how can we be assured that this is going to maintain the confidentiality, integrity, and availability of the valuable information assets that reside on that computer system? So the Orange Book dealt with security on a single box. We're also going to discuss briefly the Red Book. The Red Book talks about the network behind the individual computers. That's referred to as the TNI, Trusted Networking Interpretation. So the NCSC specifies a list or several rankings of security levels that might be required in our processing and storage of our valuable information assets. As we test and certify a computer system against this standard in the Orange Book, we can establish what we call the Trusted Computing Base at a certain level of security. Again, this identifies then a rigid boundary, or fairly well-defined boundary between what lives within the TCB and what lives outside the TCB. This boundary is called the perimeter, the TCB perimeter. And this perimeter can be penetrated only through very closely controlled and managed application programming interfaces. Remember, the communications channels that are used between layers. Well, here we have two layers. We have within the TCB and outside the TCB, and of course we then need an API so that our information can flow through that boundary and flow through a very controlled and secure manner. So here's a diagram showing components that live within the TCB. Remember, as we said before, we're talking specifically about the hardware, and that would include the firmware or BIOS that lives inside the computer system itself, and then of course the operating system that is installed on that piece of hardware. This is what lives within the TCB. And the components that are not included in this Trusted Computing Base must penetrate this perimeter, the TCB perimeter, through very carefully controlled APIs. One of the requirements of the TCB from the operating system standpoint is a kernel that protects itself, and it also has trusted recovery, trusted shell, and as it communicates with components outside the TCB, a trusted path for communication. Because if a bad guy can get between the subject and the kernel and inject his malware or violate the confidentiality or integrity or availability of the information, then the TCB is of no value. It's been exploited. So again, we need trusted path, a hardened perimeter, and system self-protection. We've pretty well defined this. This is referred to as the execution domain or a security domain. And again, what this identifies is the collection of all objects that a subject has access to. And related to processes, let's put this in perspective. Processes are only launched or can only be executed in the context of a subject's level of privilege. In other words, whoever launches the process, that process carries with it that subject's access token or level of privilege. And therefore, any of its processes run under the privilege level of whatever subject launched that process. Now, if a user launches the process, then the user's level of privilege is much smaller. The execution or security domain is much smaller. In other words, fewer resources can be accessed directly. If the kernel of the operating system launches the process, then of course the execution domain for this particular process is much larger, because the kernel is the most trusted entity on the computer system and has access to many, many more resources. And let's also remember that it is the program status word, the PSW, that is the flag that identifies which execution mode the process is going to be operating within, whether it's user mode or privileged mode. So again, the execution domain or protection domain or security domain, all three of these are the same thing. This is the collection of all objects that a subject has access to. We've defined this over and over again. So what are the objectives or the functions of the TCB? First, within the TCB, we have to, in a secure fashion, be able to launch or activate processes. This is done through that polling process we called with the interrupt requests. Then we have to identify, using the PSW, which mode of operation we're running in. Are we running in user mode, or are we running in kernel mode or privilege mode? So we have to identify which mode we're in and then properly and completely switch into that mode. Then we'll look at some memory protection mechanisms, and again, let's don't forget the trusted path requirements. As I am taking data in and outputting data, those paths of communications, those APIs, must remain secure. So, starting with process activation. Again, this is when we are trying to get a process functioning in the CPU. We want this routine to run. We want this program to run. I need my data output from this program. This is when I need it to be activated. So what happens is this process gets assigned an interrupt, and the CPU, through its polling techniques, will call that interrupt and say, do you have something for me? And because our program is ready and is waiting for the CPU to make this request, boom, our process now begins to interact with the CPU and actually gets its turn in the processing channel. When the CPU has completed all the processing for this specific process, then the CPU sets a flag again and identifies that this particular process has been completed, and will reallocate the resources that had been assigned to this process to the available pool of resources. As we recall, it was the PSW, or the program status word, that is the flag that identifies which execution domain we're going to operate in, whether it's user mode or privileged mode. And we must securely and completely switch between those two modes. Otherwise, it would be possible that a user mode process may get access to information in privileged mode, or vice versa. Both of these would be a violation of the TCB and would be a breach of security. So again, the security perimeter, this is the TCB perimeter, identifies very specifically a boundary that says these components within the perimeter have been tested and certified as maintaining a certain level of security, and anything that is not within this perimeter can only communicate with components inside the perimeter through very carefully controlled APIs or interfaces. So as we said, this perimeter can only be penetrated through very carefully controlled application programming interfaces. This API that we're talking about when it comes to a subject accessing an object is controlled by the security kernel of the operating system, and he takes advantage of another component that lives at ring 2 of in the ring architecture, called the security reference monitor. And the whole point of this evaluation through this API, as we penetrate the TCB perimeter, is to ensure that the subject who is attempting to make access of an object is doing it in an authorized fashion. And if the subject is an unauthorized subject making this request, then the request will be denied. So again, it starts with a Ring 1 executive component called the security kernel. Again, this guy is one of the main components in an operating system, and it's his job to enforce all security-related rules. He's the guy who protects the memory space for one application from another. He's also the guy that implements the security reference monitor that we're about to delineate further here. So the security kernel, a Ring 1 component, contacts the security reference monitor, a Ring 2 component, and says, we have a subject that's attempting to access an object. Is he allowed to? And the security reference monitor then looks at the process, that's the request itself, and looks at the access token that is associated with that process, who launched this process, and so we now get an identification of the subject that is making the request. Then we compare that access token to the access control list, the ACL, that lives with the object that the subject is trying to access. As these two components align, that is the subject's identity or access token, along with the ACL, the access control list of the object, we can now identify what level of access or privilege the subject has on that particular object. Again, this is very carefully controlled and monitored by both the security kernel and his worker, the security reference monitor. So this security reference monitor has three major requirements that must be in place for any operating system to satisfy any level of the TCB. The first rule of this security reference monitor is that it must provide isolation between subject and object, and it must be tamper-proof. That's rule number 1. It's a boundary between subject and object, and it cannot be tampered with. Rule number 2 is every time a subject attempts to access an object, the security kernel, security reference monitor, must be invoked and cannot be circumvented. So it's a boundary and it can't be tampered with, and it gets invoked 100% of the time, cannot be circumvented. Rule number 3 says it also must be small enough to be tested and verified completely and comprehensively. In other words, we have to be able to attest it and certify that it does provide this level of functionality, and it does it 100% of the time. So 3 rules. Again, it's a boundary and it can't be tampered with, rule 1. Rule number 2 is 100% of the accesses run through the security reference monitor and it cannot be circumvented. And then rule 3 says it has to be test-worthy. It has to be testable. And the only way that an operating system could ever comply with the requirements of the trusted computing base are if the security reference monitor satisfies these 3 rules. So let's pull this all together. Let's look at how a system provides a level of security that can be certified. So let's pull this together now and identify how a system can be certified as being trustworthy at some level of security. First, a security policy or a declaration of what level of security a system is supposed to operate at is defined, and then the system must also enforce that level of security. So it's defined in its security policy, and it is self-enforcing by the system. Second, it also identifies how these rules relating to security will be managed and how the system will protect itself, and also how it will provide the secure access to these valuable information resources. The security reference monitor is the boundary or the API that must be passed through anytime a subject attempts to access an object, and only authorized accesses will be allowed. The security reference monitor is a component of the security kernel, and he is a requirement of the operating system that, of course, is going to be evaluated against a standard in the trusted computing base. And finally, the security kernel provides access to these processes in a secure fashion. In other words, they have boundaries between them. They are isolated from one another so that these processes cannot, in an unauthorized fashion, access another process's resources. So we have boundaries between the processes. That's all within the TCB. And then we have the security reference monitor that controls how external subjects and processes access things within the TCB. And of course, the underlying operating system is self-managing.